Imagine a quiet night sky above your city. The air is still, crickets whisper, and the stars look harmless, like pinholes in a velvet curtain. Now, picture a solitary visitor sliding between those stars, a dark shard of ice and stone from another Sunday. Astronomers call it 3I Atlas, an interstellar traveler passing through our solar system. The official line says there is no danger. The orbits are mapped. The math is calm. Still, it is fair to ask, what is the true worst case? Before we begin, if you enjoy thoughtful, calming space documentaries, please tap like and consider subscribing. It helps more curious minds find these night journeys, and it lets me keep making them for you. Thank you for listening with care. You are not here for panic. You are here for clarity. The purpose of a worst case is not to frighten you, but to understand how nature works and why experts are confident. We will move slowly and keep the language simple. If a term feels heavy, we will unpack it gently. If a number sounds large, we will compare it to something familiar. This is a quiet walk through big ideas designed for easy listening. 3I Atlas is rare because it does not belong to our neighborhood. Most comets are local, icy leftovers from the edges of our own solar system. Interstellar visitors are different. They carry the fingerprints of other places and other histories. When one appears, telescopes around the world wake up. Optical observatories catch its light. Radio dishes listen for faint whispers. Space telescopes study it from above the atmosphere. With each new measurement, astronomers refine the orbit and reduce uncertainty. Every object in space moves under gravity's pull. If the path loops around the sun, it is bound. If the curve never returns, it is hyperbolic. Interstellar travelers usually ride those open curves. They swing in, feel the sun's pull, and then slip away forever. That is the normal story. Because we are exploring worst-case possibilities, we will ask what could go wrong and why the odds still remain small. Knowing the small risks is how we keep them small. Start with the fear many people hold in secret: a direct hit. In reality, the chance that any single visitor like this will strike Earth is extremely low. Space is vast, and our planet is a small target. Astronomers check constantly, updating predictions every time new data arrives. If a fresh observation nudges the path, the software adjusts, like GPS recalculating a route. Even so, it helps to picture an impact to explain how scientists reduce uncertainty step by step. What would a hit look like? Picture a block of mixed ice and rock, perhaps a few hundred meters across, entering the atmosphere at tens of kilometers per second. The speed is the danger. Even a modest object could release more energy than the largest device ever tested, all in a single moment. If it struck shallow ocean, walls of water would race outward. If it struck land, shockwaves and heat could damage cities far from the crater. These are sober facts, not predictions for tonight. There is another worry. Quieter, but real, a near miss that leaves debris in our path. As sunlight warms a comet, dust and pebbles peel away and stretch into a long stream. If Earth later crosses that stream, we get a meteor shower. Most are beautiful and harmless. In a harsher version, the stream is unusually dense. Larger fragments slip into the upper atmosphere and cause scattered damage to aircraft, power lines, or ground structures. This remains unlikely, but it belongs on a complete checklist. Paths can drift in small ways. Sunlight can push a comet the way a breeze moves a sailboat. Outgassing adds another push, as frozen gases warm and puff from vents in the surface. Over weeks and months, these effects can shift timing and aim by tiny amounts. Astronomers include these nudges in their models and tighten predictions with better data. Radar, when available, gives very precise distance and speed. The better we know position and velocity, the clearer the future path becomes. There is also the human worst case. Even with no danger, rumors can outrun facts. A single uncertain measurement can grow into fearful headlines. In a loud moment, bad information creates panic buying, traffic problems, and sleepless nights. The harm would not come from the comet. It would come from us. The antidote is simple and strong: clear communication, patient updates, and trust in independent checks. What keeps professionals calm is redundancy. Many telescopes, many nights, many teams. When one group reports a position, another checks it. When one program predicts an orbit, a second verifies it. If the numbers ever hint at risk, the next steps are clear. Focus more telescopes, call in radar, refine the models, and repeat. The goal is not a dramatic move. The goal is the next measurement, and then the next, until the picture is sharp and the worry shrinks. For now, settle in. Breathe slowly. The sky is vast, the tools are good, and most stories in astronomy end not with disaster, but with understanding. 3i Atlas may be a stranger, but strangers become familiar when we take the time to see them clearly. Tonight, we begin that careful look. Think of space as a giant, dark ocean, and our instruments as lighthouses along a shore. When 3i Atlas first appeared, it was just a faint speck moving against fixed stars. Astronomers compared pictures taken minutes and hours apart. The speck shifted a little each time. That motion gave away its path. With every new image, the orbit became less fuzzy, like bringing a distant ship into focus. An interstellar comet follows an open curve. It does not loop back. That shape tells us it is not bound to the Sunday. The speed is another clue. Even far from the sun, it moves faster than local comets usually do. That extra speed is called excess velocity. You can imagine it as leftover momentum from another star system. It is the reason 3i Atlas will visit and then leave forever. How do scientists turn faint dots into confident predictions? First, they log positions on the sky, which are simple angles. Then they measure distance, sometimes by clever geometry, sometimes with radar if the object is close and bright enough. With position and distance over time, they map the three-dimensional path, add velocity, which is how fast and in what direction the object moves, and the future becomes a calculable story. Small pushes complicate that story. A comet warms near the sun and vents gas and dust. Like a slow leak in a tire, those puffs act like tiny thrusters. Sunlight adds another push. Over weeks, these forces shift the path by short distances that matter a lot to forecasters. To handle this, teams build models that include outgassing and sunlight pressure. They update the model each time new data arrives. This is why professional updates often sound repetitive. The repetition is the safety. Now let's explore worst-case ideas with calm logic. Start with gravitational trouble. Could 3i Atlas fly near a planet and get slung into a sharper path toward Earth? In theory, gravity assists can bend a trajectory. In practice, the aim would need to be unbelievably precise. Planets are far apart. Their safe zones are large. Their dangerous bullseyes are tiny. Because the object is already moving fast on a one-way curve, a dramatic redirect into an impact is not impossible, but the odds are so small that mission planners would call it negligible. What about stirring up fragile things at the edge of our system? Like the Oort cloud, that distant reservoir of icy bodies is real, but it is unimaginably far away. One passing visitor does not kick it like a hornet's nest. The scales are too large. If you touched a lake with a single finger, you would not expect a wave to flip boats on the far shore. The same intuition works here. Another worst-case idea is a hidden split. Comets can fracture as they warm. A single body might become a cluster of fragments. Could a quiet visitor turn into a messy cloud? It could. Fragments change the problem, but they usually spread along the same path like beads on a string. That makes the stream easier to predict, not harder. In a severe version, a large chunk could drift off the main line. Even then, the same tracking tools apply. Astronomers would notice the split, measure each piece, and refine the map. There is also the fear of an outburst. Comets sometimes flare as pockets of gas erupt. An outburst can brighten the coma and push the nucleus slightly. That push is small compared to the vast distances involved. It may shift timing by minutes or hours weeks later, but not flip a safe miss into a surprise bullseye. The cure is simple. Watch carefully. Update the math. If a nudge occurs, the new path will show it. Suppose, despite all this, a worrying scenario appeared. What then? Planetary defense is a real, active field. The goal is to find hazardous objects early and, if needed, deflect them. The fastest option is a kinetic impactor, which is a focused collision by a robotic spacecraft to change the target's speed by a tiny amount. That small change, applied early, turns into a big miss later. Another idea is a gravity tractor, where a spacecraft hovers near the object and uses its own gravity as a gentle tug. For comets that vent gas, warming the surface unevenly with a laser or a reflective sail could add a controlled push. Some of these methods are already tested in principle. Others are in planning and simulation stages. The core point is that time is our friend. The more warning we have, the gentler the fix can be. But what if time were short? Then, civil defense matters. Even without deflection, we can predict where fragments or shockwaves might land. We can move people, protect power grids, and secure water systems. Quiet planning saves lives. The world does this for storms and wildfires. We could do it for a rare celestial event too. Here is a useful mental model. Risk equals hazard times exposure times vulnerability. The hazard is the raw physical threat. Exposure is how often and how directly we meet it. Vulnerability is how prepared and resilient we are. Interstellar comets carry some hazard because they are fast and massive. Exposure is low because they are rare and space is big. Vulnerability is lower today than decades ago because our survey networks are sharper, our computers are faster, and coordination across space agencies is better. When you multiply those factors, the result is small. That is why professionals can be calm without being careless. Through all of this, remember the human layer. Rumors fill silence, so professionals avoid silence. Regular, plain updates matter. It is better to say we are still watching and the path is still safe, than to say nothing and let fear invent a story. Independent teams compare notes. Space agencies post their data. Amateur skywatchers check with their own telescopes. The overlap builds trust. In the next stretch of our journey, we will slow down and imagine the physical details of a hypothetical impact, not to scare, but to translate energy and speed into everyday pictures. By doing so, we will also see why most outcomes remain ordinary. The night is patient, the science is steady, and the visitor is most likely only that, a visitor, here for a brief hello before the long road out. Imagine time paused, and a virtual camera above Earth. Far out, a charcoal gray object, about the size of a city block, falls along a steep path. It is dull and cold, like an unlit coal. As it nears sunlight, pockets of ice hiss, dust drifts off and forms a faint tail. None of it matters, until the object meets the upper air. Two broad outcomes exist: an airburst or a ground strike. In an airburst, the body breaks high in the sky and dumps its energy in a single hot pulse. Windows pop, sonic waves roll across neighborhoods, bright fragments fade before reaching the ground. In a ground strike, the core holds together long enough to hit. The shock is focused, a crater opens, and debris flies out in a ring. Which path occurs depends on size, strength, and entry angle. The atmosphere is a cushion. Small stones skip and burn, larger bodies punch deeper. Speed is the great amplifier. A car at city pace is gentle. The same car on a highway is dangerous. Near Earth, a fast visitor moves many times faster than a rifle bullet. That speed turns mass into punch. No equations are needed. Picture a hammer. Now, picture the same hammer swung by an elite athlete. The tool has not changed. The energy has. A rough timeline helps. Hours to days before closest approach, astronomers publish refined coordinates and confidence windows. If risk grows, emergency managers run location-based scenarios. Airlines reroute long flights. Power utilities prepare to isolate lines if a shock-induced surge seems possible. Hospitals check backup systems. It is the same careful choreography used for hurricanes and wildfires, except the trigger is above us, not along a coast. Now entry. A few hundred kilometers up, the object meets thin air. The air in front compresses and heats to thousands of degrees. A glowing sheath forms and the sky paints a white-green streak. If the body is fragile, it begins to crack. Cracks peel. The peel becomes a break, and the break blossoms into a bright flower as an airburst releases its energy. From the ground, an airburst arrives in two acts. First light, then sound. People see a brilliant flash and a long, luminous train, like a camera flash smeared across the sky. Minutes later, a deep rolling boom rattles windows. In the worst version, if the body is large, the shock can injure people near glass or outdoors. Buildings themselves, unless very close, usually endure. The damage pattern is scattered and mostly from glass and falling objects. A ground strike is different. Imagine a white disk racing downward, then a blinding flare at the surface. A column of dust rises, shockwaves knock down trees and weak structures in rings. Closer in, heat can ignite brush. Even a modest crater can be larger than a football stadium. Ejected material lands kilometers away. Lakes can slosh. Shallow seas can throw up walls of water. The loudest sound is over in seconds, but echoes in the air and ground linger. In both cases, Earth behaves like a drum. Pressure waves circle the globe and return. Sensitive barometers see the signal pass more than once. On the ocean, those waves barely disturb the surface. In the air, they can be measured from far away. Satellites record the thermal flash. Weather radars map the dust plume. A surge of videos helps experts triangulate height and angle and refine models in real time. What about toxic fallout? Comets are mainly ice, dust, and rock with traces of organic molecules. They are not chemical weapons. The main health risks are broken glass, fire, dust inhalation near the strike, and second-order effects like power loss or traffic snarls. With prompt guidance and simple steps like moving away from windows and keeping roads clear for responders, many injuries can be prevented. Water adds a special case. If a fragment hits shallow coastal ocean, a local tsunami can form. It is not a giant basin-wide wave like a massive earthquake, but it can flood harbors and low-lying neighborhoods. The same sirens and route maps used for storm surge would serve. Ships head to deep water. People in flood zones move to higher ground, following plans coastal cities practice every year. How much warning would ordinary people get? Today, quite a lot compared to past decades. Sky surveys run all night in both hemispheres. Automated software flags moving points and passes them to human reviewers. When an object looks interesting, follow-up begins within hours. Space agencies publish updates in plain language. Newsrooms have learned to cover these events without turning them into panic. Science communicators act as bridges, translating jargon into calm steps. Fold this back into the worst-case frame and a few truths stand out. Truly large global events are rare and would almost certainly be seen well in advance. Medium events that can damage a region are survivable with planning and clear information. Small events are noisy and bright, but they mainly teach us. They give us practice and remind us that Earth lives under a sky alive with motion. Remember what large numbers can hide. A 1 in a million chance sounds tiny until the stakes feel personal. The key is proportion. We accept familiar risks because we understand them, like driving to work or walking in a storm. Space adds one more. By thinking through the details with a calm mind, we turn a nameless fear into a known quantity. Known quantities can be managed. Unknowns loom. Next, we will look at how the orbit of 3I Atlas is pinned down in practice, and how independent teams cross-check one another so that even surprising behavior does not slip by unnoticed. The sky is not a threat by nature. It is a system. Systems can be watched, measured, and understood. That steady truth runs through this entire story. Picture a mapmaker with a pencil, shading a small oval on a star chart. That oval is the uncertainty window for 3I Atlas. At first, it is big. Each new observation shrinks it, like tightening a camera focus. This is orbit determination in plain terms. You start with where it is on the sky, add when it was seen, then fold in how fast it seems to move from one image to the next. With enough nights and enough telescopes, the fuzzy oval collapses into a thin line you can trust. Who does this work? A global relay team. Survey telescopes scan wide fields all night, flagging moving points. The Minor Planet Center acts like an air traffic hub, collecting reports and distributing them. Dedicated follow-up scopes zoom in for precision. Big observatories add detail when the object is bright enough. Public groups and university teams contribute too. Redundancy is the safety net. If clouds shut down one site, another site keeps the threat alive. Under the hood, the math has a humble heart. It is all about position, velocity, and gravity. The software fits a path that best explains the whole set of measurements, and then it asks how wrong that fit could still be while matching the data. Think of drawing a best fit line through dots on paper, then sketching faint lines above and below to show possible alternatives. Those faint lines are the uncertainty bounds. They matter as much as the central answer. Sometimes the sky makes things hard. The object can drift into the sun's glare. That does not mean the track is lost. Forecasts carry the path forward until it emerges again into the dark. Teams plan recovery observations the moment geometry improves. Radar, when possible, changes the game by giving direct distance and speed to many decimal places. Even brief radar echoes can shrink uncertainties that optical light alone cannot. When radar is not an option, timing and coordination fill the gap. A favorite tool is the clone swarm. Computers create thousands of slightly different versions of the same orbit, all consistent with the data so far. They then roll those futures forward to see where they spread, and whether any skim close to Earth. If a handful wander into worrisome distances, the team hunts for the one specific new observation that would separate the safe futures from the risky ones most quickly. This is targeted observing. It saves time and calms nerves. Now fold this process into the worst-case mindset. What if 3I Atlas becomes active and outgasses strongly, changing its path by small, random pushes? The answer is not drama, it is cadence. Observe, update, repeat. Models that include gentle thrust from sunlight and escaping gas are already standard. If an outburst happens, the light curve spikes, warning everyone. The next few nights of data tell you whether the push was significant. If it was, the uncertainty oval grows for a moment, then shrinks again as measurements pour in. What if it fragments? Telescopes would see a blur become 2 points, then more. Each point gets its own track. The clones split too, now mapping futures for each fragment. In practice, fragments spread along the same general highway, which keeps the prediction problem manageable. The side effect is actually helpful for risk assessment. A broken comet makes more light, and more light makes it easier to track. There is a quiet strength in how independent these checks are. Different software packages, different observatories, different national groups. They compare without needing to agree by design. If one group sees a nudge, the others either confirm it or fail to reproduce it, and everyone looks again. The culture rewards caution. When people say there is no known threat, they mean many eyes ran many tests and found the same calm answer. History offers a useful memory. Years ago, an asteroid named Apophis briefly showed a worrying chance of impact far in the future. More data erased that worry. The lesson was not that the early alert was wrong. The lesson was that early alerts are supposed to trigger better observations. As the data improved, the picture sharpened, and the risk faded. That is the pattern to expect here, too. Big uncertainty at first, then a downhill slide toward clarity. Communication is part of the system. Space agencies and research centers publish updates in plain language alongside technical tables. They include the date, the number of observations, and how far the uncertainty has dropped. Good updates explain what changed and what did not. They avoid heat, they stick to light. This steady tone helps prevent rumor storms from forming when a graph wiggles. One more layer sits behind the scenes: simulation drills. Planetary defense teams run tabletop exercises that mix realistic sky alerts with decision-making. They practice what data they would request, who would coordinate airspace, how utilities would prepare, and how to brief the public. These rehearsals mean that, even in a rare tense week, the people in charge have a playbook ready. All of this makes a worst case less mysterious. The danger does not sneak in silence. It would announce itself through measurable changes: a brightening, a path shift, a fragment train. Those changes would trigger denser observations, which would either confirm a problem or quickly rule it out. If a problem survived scrutiny, options would line up: more tracking, precise forecasts, civil protection steps, and, if time allowed and the target were suitable, a deflection concept. Most likely, none of that will be needed. The visitor will arc in, warm, breathe a little dust, and slip back into deep space. Still, walking through the process gives peace of mind. You now know how the map is drawn, how the pencil marks tighten, and how many hands check the work. Uncertainty is not a monster. It is a number that shrinks with patience. In the next chapter, we will imagine a detailed but hypothetical chain of events where early measurements hint at danger, and we will follow the full decision tree from the first alert to the all clear. Not to add fear, but to show how resilience looks in motion, step by step, night by night. Imagine a quiet Tuesday just after midnight. An automated survey telescope in the southern hemisphere finishes a scan and flags a fast-moving point. The software notes something unusual about the speed and direction. An observer on duty double-checks, submits the measurement, and tags it urgent. Within minutes, the report lands at the central clearinghouse, where many such points arrive every night. Most turn out to be routine near-Earth asteroids or distant comets. This one looks odd enough to deserve follow-up before dawn. Hour 1. A second observatory picks it up on short notice. The point has shifted exactly as predicted from the first note. That small agreement is a big deal. It means the object is real and fast. Alerts go out to a prearranged list. Teams in other time zones prepare to catch it at their sunrise. Everything is quiet, methodical, almost boring in its professionalism. Hour 6. 3 more observatories add positions. Early math suggests an interstellar origin and a path that will cross the plane of Earth's orbit in a few weeks. That phrase is dramatic if you do not live in this world. For astronomers, it simply means the object will pass through the flat disk where Earth and the planets move. Space is still mostly empty. Even so, The phrase puts this visitor into a higher priority lane. The uncertainty oval is large, but it has to be treated with care. Day 1. The first public note appears. A new interstellar candidate with a preliminary path. No threat indicated. Teams request more observations over the next 48 hours to tighten parameters. If you could stand in the control rooms, you would hear calm voices, short acknowledgements, the click of shutters, and the gentle drone of cooling fans. No rushing, just cadence. Day 2. A small wobble appears in the fit. It could be measurement, noise, or a hint that outgassing is already nudging the path. The cure is always the same. More data. The clone swarm spreads out possible futures like a fan of thin threads. Most miss Earth by a wide margin. A tiny fraction brush closer than comfort. That does not mean danger. It means your map needs another pin. Day 3. Radar options are considered. If geometry allows, a powerful dish can send a pulse and listen for the echo. Distance and speed drop out with beautiful precision. Suppose in our scenario the object is still too far and faint for radar. The plan shifts to optical timing. Multiple sites track it continuously through a long arc of sky. Schools and amateurs contribute useful points from smaller telescopes. Each clean position shaves a thin layer off uncertainty. Day 4. A press update explains the state of play in plain language. The visitor is likely interstellar. It remains on a safe path, but teams are watching closely, because early outgassing can add tiny pushes. The next step is more tracking through the weekend. The tone is steady and transparent. That tone is not a detail. It is part of risk management. Good information keeps rumor from filling the gaps. Day 5. A mild outburst brightens the coma. The light curve jumps, then settles. Models adjust to include a small, non-gravitational push. The clone swarm tightens again. The few thin threads that once grazed Earth drift away from the hazard zone. Risk falls, not because anyone waved a wand, but because the map got sharper. Day 6. A new worry appears. Not in the sky, but online. A viral post claims a cover-up and insists the object will hit. The post cites no data, offers no uncertainties, and spreads anyway. The response is not to argue in the same tone. The response is to post fresh facts, exact times of the next observations, who is taking them, and when the next update will arrive. Calm schedules do more to diffuse panic than emotional replies. Day 7. A major observatory gets a long, clean track in dark, dry air. The fit becomes elegant. The speed says interstellar beyond reasonable doubt. The path swings inside the orbit of Mars and out again, missing Earth by a safe margin measured in millions of kilometers. The update uses familiar comparisons. If Earth were a coin, the visitor would pass many city blocks away. Not close, not grazing, far. 8. Teams run a tabletop drill anyway. The question is not what to do now, but what they would do if a future object followed a sharper, riskier path. The drill covers who would brief air traffic regulators, how power grids would harden, which coastal cities would stage equipment on high ground, and which satellites would watch. Practicing in peacetime is how you stay calm in any storm. Day 9. The sky itself tells the rest of the story. The visitor brightens gently as it nears the sun, sheds a thin ribbon of dust, and then fades. Meteor scientists project the dust stream's future and find no dense crossing with Earth. That means no unusual meteor shower months later. Pilots and satellite operators get routine notes anyway because it is good habit to share awareness, even when the answer is no action needed. Now zoom out and look at the whole chain. At each fork, the system offers a next step that reduces uncertainty. Find it, track it, update, communicate, repeat. Notice how the worst case never appears in a single leap. It would have to climb a ladder of evidence, a persistent path toward Earth inside the uncertainty bounds, a measured non-gravitational push that bends closer instead of wider, a lack of radar that demands optical precision and gets it anyway. At any rung of that ladder, better data can lower concern. If concern rises despite better data, options open in proportion to warning time. Civil protection, rerouting, even a study of deflection if the target is suitable and the calendar is long enough. Even the human side follows a decision tree. If rumor spikes, increase cadence of updates. If a term confuses people, define it with a picture, not a formula. If a fake timeline circulates, publish the real one with timestamps. One quiet truth runs through it all. Fear thrives on blank space. Facts, posted on time and in plain words, fill that space with light. Finally, bring it back to the bedside listener. You are not expected to remember names of telescopes or acronyms. What matters is the rhythm. Professionals watch the sky every night. When something unusual appears, they close ranks across countries and time zones, tighten the math, and speak simply about what they see. In our scenario, the answer ends the way most do. The visitor pays a brief, beautiful call and continues its long journey. We are left with more practice, better tools, and a little more humility before the ocean of space. In the next chapter, we will look at the physics inside a comet itself, how sunlight wakes it, how jets form, why some nuclei hold together while others crumble, and what those details mean for forecasting. The closer we get to the object's true nature, the clearer every downstream decision becomes. Think of a comet's heart as a dirty snowball that grew up in deep space. Astronomers call that heart the nucleus. It is usually a few hundred meters to a few kilometers across. The surface is dark, closer to charcoal than fresh snow. That darkness matters because it lets sunlight warm the surface efficiently. When the surface warms enough, ices near the top layer turn straight into gas. That gentle boil is called sublimation. Gas escapes through pores and cracks, carrying dust with it. The gas and dust spread around the nucleus like a thin, glowing atmosphere. That glow is the coma. A steady solar breeze pushes the lightest bits into a long tail. Not all ices wake up at the same distance from the sunday. Water ice needs more warmth, so it becomes active closer in. Carbon monoxide and carbon dioxide can turn to gas farther out. In colder regions, this mix gives each comet a personal rhythm. Some wake early and stay lively. Others sleep until they cross a warmer zone, then throw a brief, bright tantrum. Forecasting depends on learning a comet's rhythm quickly, then adjusting as new behavior appears. Jets are the comet's breath. Imagine sunlight hitting a patchwork surface. One spot has a thin crust. Beneath it sits ice, ready to vaporize. As heat sinks in, pressure builds, the crust cracks, and a narrow jet of gas shoots out. That jet acts like a tiny thruster. It can change the comet's spin a little and nudge the path by a tiny amount. These nudges do not send a comet across the solar system in a new direction, but over weeks, they can shift timing by minutes or hours. Observers watch for jets by studying brightness close to the nucleus and by tracking subtle changes in the light curve, which is a simple graph of how bright the object looks night after night. Strength is the quiet player. Many comet nuclei are weak, more like a loosely packed snowbank than solid rock. Scientists describe this with the phrase low tensile strength. It means the material cannot resist much pull. As a comet spins, that weakness can matter. If sunlight speeds up the spin slightly, the nucleus can begin to shed material at the equator, like a slow-motion dog shaking water from its fur. In extreme cases, the body fractures. A split is dramatic in pictures, but straightforward to model. The fragments usually line up along the path like pearls on a string. Each one gets its own track and its own small set of jets. Temperature stress adds another path to trouble. The sunlit side warms, the night side stays cold. On a rotating body, those extremes swap every few hours. Repeated heating and cooling opens new cracks, exposes fresh ice, and feeds more jets. None of this is mysterious. It is the same everyday physics of expansion and contraction, played out on a stage of ice, dust, and vacuum. What do astronomers measure to decode all this? Color and brightness tell us about dust size and how much sunlight the surface reflects. Spectra, which are just light split into a rainbow, reveal what gases are leaking out. Simple fingerprints in that rainbow say water is present, or carbon dioxide, or carbon monoxide, or even simple organic molecules. When gas production rises, non-gravitational pushes grow too. Orbit models include terms for those pushes. As data improves, the model learns how strong the jets are, and predictions tighten. Tides enter the story near close passes. If a weak comet swings too near a planet, gravity can stretch it. That stretch is a tidal force, the same family that moves Earth's oceans. Most interstellar visitors do not thread those narrow needles. The geometry would need to be very unlucky. Still, it is on the checklist. If a tight pass ever appeared in forecasts, observers would prepare for a higher chance of shedding or splitting and would watch for new fragments. Dust-to-gas ratio is a practical phrase you may hear in updates. It simply asks whether a comet releases more dust than gas, or the other way around. Dusty comets brighten strongly because dust reflects sunlight well. Gassy comets can show dramatic jets in spectra even if the visible glow is modest. For predicting risk, Dusty streams matter because they later become meteor showers. Again, most streams are thin and harmless. Forecasts flag denser ones if they appear. Rotation is both a clue and a lever. By watching small dips and rises in brightness within a single night, astronomers can often infer how fast a comet spins. A slower spin tends to be calmer. A faster spin raises the odds of shedding. If the spin rate changes over days, jets are torquing the nucleus, which helps refine those non-gravitational terms in the orbit model. All of this flows back into timing predictions and safe distance estimates. From a worst-case point of view, 3 internal events would raise eyebrows. First, a sustained outburst that keeps a high gas output for many days, raising the chance of meaningful path nudges. Second, a major split that sends a large fragment onto a slightly different track. Third, a rapid spin-up that hints the nucleus is near its structural limit. None of these events instantly creates a disaster. Each one simply triggers denser observations and tighter modeling. The loop remains the same. Watch, measure, update, repeat. There is comfort in how quickly the sky tells on itself. A brightening coma shows up in hours. A new fragment is obvious, even in modest telescopes. A spin change appears in the nightly light curve. Nothing hides for long. This is why professionals sleep at night, even during interesting weeks. The physics is noisy, but it is not secretive. Bring this back to 3I Atlas. As an interstellar visitor, it likely carries a different blend of ices and dust than most local comets. That is part of the scientific gold. By sampling its light, we learn about chemistry in another star's nursery. By tracking its jets, we learn how fragile bodies behave at high speeds on open, one-way paths. The same data that makes good science also makes good safety. The tools do double duty without extra effort. In the next chapter, we will walk through a full hypothetical chain where a fragment separates, a jet nudges the timing, and air traffic controllers, satellite operators, and power utilities receive precise, calm guidance based on those changes. You will hear the language used, the timelines given, and the practical steps taken on the ground, so the picture of readiness becomes concrete and human. Dawn breaks over 2 continents when a monitoring team notices something strange. The point of light that was 3I Atlas looks slightly stretched in a fresh series of images. Within an hour, higher resolution shots confirm it. The nucleus has split. 2 cores now glow inside the same fuzzy coma, the second one fainter and a few dozen kilometers behind the first along the flight path. The discovery travels through the network in minutes. A short bulletin goes out with 3 facts in plain language. A fragment has separated. Both pieces stay on the general safe path. More observations tonight will tighten the details. The first task is naming and tracking. The brighter core keeps the original label with a tag A. The newcomer gets tag B. Each receives its own predicted positions and uncertainties. Computers generate clone swarms for both. The aim is to learn whether the small separation plus any jet activity could change timing in a way that matters. Because the fragments are strung along a single highway, the most likely change is that one arrives a little early and the other a little late relative to the single-body forecast. During the next night, observers gather a clean set of positions through a long arc of sky. The fits look good. The secondary fragment is shedding dust faster, which means stronger jets and slightly larger non-gravitational pushes. The model assigns a modest thrust to B and a gentler one to A. The result is simple. A leads, B lags. The gap in arrival times at the plane of Earth's orbit grows from minutes to perhaps an hour. Missed distances remain large. The map is calm. Even so, the split triggers a useful chain of coordination. Air traffic centers receive a routine notice, reminding them of the predicted radiant of any meteors tied to the dust stream, should a thin stream form later. For most routes, the note is academic. Crews keep the same procedures they already have for rare, bright meteors. Satellite operators receive an update on expected dust density at orbital altitudes. The forecast shows a thin environment. No avoidance maneuvers are recommended. Ground power utilities receive a memo that ties the comet timeline to normal space weather bulletins about the Sunday. The point is not that the comet threatens grids. It is that agencies use the same message lanes to keep everyone synced to one set of clocks. On the human side, public updates emphasize the pattern. Fragmentation is common in weak comets. 2 beads on a string are easier to track than one blurry peanut. The new data narrows uncertainties. The miss remains wide. Journalists get a simple image comparing last night and tonight. The second point is obvious, even to a casual eye. Confidence rises because the sky has told on itself, and the measurements match the picture. 2 days later, a new wrinkle appears. The fainter fragment flares. For about an hour it brightens by a factor of a few, then calms. That flare means a jet turned on, like a vent opening when sunlight hit a fresh crack. The effect on the path is tiny but measurable. The predicted time B crosses a reference plane shifts by a handful of minutes. The network treats it as a rehearsal of a rougher case. How fast can a clean measurement roll through models and reach people who might care? The answer is faster than most imagine. Observatories upload time-stamped images as they arrive. The FIT software digests them and spits out an updated set of positions and velocities. The clone swarm for B shrinks. The central service posts an updated table with a clear revision mark and a short description of what changed. An email with a link and a one-sentence summary lands in the inboxes of airlines, satellite teams, and utilities that opted into the list. For most of them, the update is a non-event, but trust grows because the pipe works. To make the exercise real, air traffic controllers run a low-key drill. They simulate reports of a bright fireball over empty desert at the predicted radiant and time, even though nothing unusual is expected. The drill tests how quickly crews would route around any potential airburst zone if one ever mattered. The output is a checklist: who calls whom, which reroutes are favored, how to avoid crowding a narrow corridor. The drill finishes in less than an hour and returns to standby. Nothing flashy, just muscle memory. Satellite operators run their own check. They test how long it would take to update tracking of a diffused dust sheet, if one existed, and whether any planned engine burns would need a tweak. The answer is that their normal cadence is enough. They also verify that their sensors would see a dust thickening days in advance. Eyes open, no changes needed. Power grid planners take the chance to tie this storyline to their usual space weather posture. They confirm that any geomagnetic storm alerts would still come from solar monitors, not from the comet. They make sure their control rooms know the comet's schedule, only to prevent confusion if a bright meteor event leads to calls from the public. Clear lines avoid mixed signals in busy rooms. As the days pass, the two fragments continue their quiet ballet. A remains the anchor. B breathes out sporadically and drifts a little more behind. The dust they shed paints a thin ribbon that models predict will miss Earth by a comfortable margin. Meteor scientists put numbers on the peak rate should any stray particles intersect the upper atmosphere months later. The figures are low. If anything, skywatchers may enjoy a few extra streaks long after the visitor has gone. When the date of closest approach arrives, the show is pretty but ordinary. The brighter core glows in binoculars from dark sights. The fainter one is a challenge even for modest telescopes. Social media fills with pleasant images, not alarm. A closing update thanks the observatories, lists the total number of measurements, and shows how the uncertainty band shrank from wide to thin over the week. The figure is satisfying to anyone who watched the story unfold. What did this teach us about a worst case? That a fragment and a jet are not dramatic by themselves. They are part of a language that the sky speaks, and that we now translate quickly. The translation chain begins with a photon on a sensor, and ends with a simple sentence to a pilot or an engineer. The less poetry in that sentence, the better. Clear words on time are the real safety system. In the next chapter, we will step back and ask why interstellar visitors like 3I Atlas are so fast, how their speeds shape both risk and beauty, and what that speed tells us about the invisible highways that connect stars. Speed is the quiet headline of every interstellar story. Local comets meander around the sun like slow traffic on a neighborhood street. Interstellar visitors arrive like express trains. Their extra speed is called hyperbolic excess, the leftover momentum they carry from long before they met our star. It is why their paths are open curves, not loops, and why their hello is brief. How fast is fast? Picture Earth's escape speed, the pace you must reach to break free from the sun at Earth's distance. Interstellar objects coast in already above that mark. Even far from the sun, they cut through space at tens of kilometers per second. Near perihelion, the closest point to the sun, they move faster, like a skater dropping into a bowl and shooting out the other side. Speed shapes risk, beauty, and science all at once. It raises the energy of any impact, which is why worst-case thought experiments take it seriously. It also stretches and brightens the tale as expelled dust meets a stronger solar wind, and it helps scientists measure composition. Fast jets can tug the nucleus more, which makes non-gravitational effects easier to detect in the numbers. Where does that speed come from? Start the clock far away, in the birth cloud of another star. As planets form, countless icy scraps get tossed around by gravity. Most settle into stable homes. Some are thrown out, like pebbles flicked from a wheel. Those ejected pieces inherit the speed of their old system plus whatever kick the slingshot gave them. They wander the galaxy on long arcs, until chance steers one into our neighborhood. Now picture the galaxy itself as a slow river. Our sun orbits its center. Other stars do too, each with its own gentle drift. When a visitor comes, its speed relative to us is a blend of its own motion and ours. If we happen to be moving in similar directions, the closing speed is modest. If we are on crossing lanes, the speed is larger. This is why interstellar visitors arrive with a range of velocities and approach angles. It is traffic, but on a cosmic highway. Gravity along the way can add spice. A visitor threading through the outer planets can gain or lose a little speed and steer by a few degrees, much like a spacecraft under a planned gravity assist. But because interstellar objects start out fast and the distances between planets are huge, these tweaks are small. A dramatic bend into a collision path would require a near-magic combination of timing and aim. The space between the bullseyes is vast. Speed also sets the clock for observers. A slow asteroid can be watched for months before it reaches its closest point. A fast interstellar comet can cross the inner solar system in a fraction of that time. That means survey networks and follow-up teams move in a brisk cadence. Early notice is precious. The faint speck detected weeks out yields more nights of data than the same object spotted late. This is why the worldwide habit of scanning all night, every clear night, matters. From a worst-case standpoint, speed narrows windows but does not remove them. Even a fast mover takes days to cross from one planet's orbit to the next. Each day is a chance to refine its track. When brightness allows, radar compresses uncertainty by orders of magnitude in a single session. When it does not, coordinated optical timing fills the gap. Either way, the clock is brisk but not frantic. The same speed that makes a potential impact energetic also redistributes its likelihood. A faster object spends less time near Earth. It streaks through the crossing point and is gone. The brief overlap reduces exposure, one of the three parts of risk. Hazard may be high on a per-impact basis, but exposure is lower. This is one reason experienced teams can talk about worst cases calmly. There is a kind of beauty to the way velocity paints the sky. A fast nucleus throwing off dust meets the solar wind like a boat meeting a current. The tail streams out, bends gently, and sometimes shows ripples where gusts in the solar wind pass by. In long exposures, the motion writes a graceful arc. In binoculars from a dark site, a quick visitor can look like a ghostly torch. For planning, timing rules everything. If a visitor will sweep through the plane of Earth's orbit on a particular date, agencies attach that date to a clear schedule. When the next update will post, when pilots should expect a routine advisory, when satellite teams should check their sensor logs for streaks, and when the public can expect the all-clear. These timestamps are powerful. They give people something to hold instead of rumors. There is one more reason velocity helps rather than harms. It makes deflection, if it were ever needed, an earlier conversation. The faster an object moves, the earlier you must act to make a small change spread into a safe miss. That pushes preparation toward better surveys, faster pipelines from detection to modeling, and regular drills. All of those are good investments, even when no deflection is required. In the end, speed is not the villain of this story. It is a feature of a living galaxy. Stars orbit, icy shards wander. Some pass near us quickly. We study them, learn from them, and watch them go. Worst-case thinking respects velocity because it magnifies energy, but it also respects the tools that turn fast events into clear answers. Constant surveys, rapid data sharing, and updates posted on time. As 3I Atlas rushes through its arc, remember the simple picture. The object is a visitor on an express lane. Our instruments are lighthouses keeping pace. The ocean is vast, the beam is steady, and the ship will pass. What remains is knowledge and a little shared awe at how speed reveals the shape of space itself. Imagine invisible highways threaded through space. They are not roads, but patterns made by gravity. Every star, planet, and shard of ice travels along these patterns. When we say 3I Atlas follows an open curve, we mean it is sliding down one of those invisible lanes. If you could dust the galaxy with chalk, you would see countless arcs crossing and bending, a soft lattice of motion. The beauty is that simple rules draw these lanes. Mass attracts mass. Faster paths curve less. Slower paths can be captured. From these quiet truths, everything else flows. One helpful idea is gravitational focusing. Picture Earth as a small circle and gravity as a gentle magnifying glass that bends passing pebbles slightly inward. Because of that bending, a narrow stream of particles behind the Earth is a tiny bit denser than in front. This is not a threat by itself. It is a way of seeing that gravity acts like a lens, changing aim by small amounts. For fast interstellar objects, the lensing is weaker because speed gives them more inertia. They ignore the invitation to linger. They bow politely and continue on. Another guidepost is the sphere of influence. Around each planet there is a bubble where the planet's gravity matters more than the sun's. Spacecraft navigators use that bubble to plan flybys. For a fast visitor, this bubble is small in time. Even if it is big in distance, passing through it is like stepping on a moving walkway for a heartbeat. You feel a nudge, then you are gone. A wild redirect into danger would demand a perfect thread through a tiny keyhole. Space is too large and timing too delicate for that to happen often. Now fold these lanes into human systems. Think of 3 rings of watchfulness. The first ring is discovery. Wide-field surveys scan the sky, hunting for motion against the fixed background. Automation flags candidates, and people validate them. The second ring is characterization. Follow-up telescopes measure brightness, color, and the subtle twists that reveal spin. Radar, when in range, pins down distance and speed with crisp precision. The third ring is communication. A few clear pages tell pilots, satellite teams, utilities, and the public what matters and when. The rings overlap by design. If one ring stumbles, another fills the gap. Because your goal is calm understanding, let us imagine a tidy decision tree that could apply to 3i Atlas or to any future visitor. Step 1 is classification. Is it interstellar? The answer comes from speed and the shape of the path. Step 2 is proximity. How close will it pass to Earth, and when? Step 3 is activity. Does it shed dust, flare, or fragment? Step 4 is consequence. Could dust cause a meteor outburst months later? Could the path shift enough to raise concern? Each yes triggers more focus, not fear. Each no keeps the process lean. People often ask about surprises. Could the object hide a hollow core that collapses late? Could a jet awaken on the far side and push harder than expected? Could a small fragment separate and head our way? The honest answer is that nature can still startle us, but not for long. Hidden hollows reveal themselves as the light curve wobbles. New jets change the timing, and that change shows up in the next batch of measurements. Fragments are bright dots, even in modest instruments. Surprise is a door that opens often, but behind that door we find more data, not secrets. There is comfort in the way timing rules the human side. Updates can be posted at the same times every day, even if nothing changes. A line that says, "No change" is powerful. It closes the room to rumor. If a change does appear, the update can show before and after in one small graphic. Arrows mark the difference. A sentence explains it in plain words. The audience includes pilots, engineers, school science clubs, and night sky fans. Writing for all of them at once rewards clarity. It also helps to keep metaphors gentle and consistent. Calling the object a visitor reminds us that most visitors leave without trouble. Calling the orbit a lane reminds us that motion follows rules. Comparing a fragment train to beads on a string makes a complicated image easier to hold. These pictures are not decoration. They are tools that let a wide audience share the same mental model as the experts who watch all night. Let us return to worst-case thinking for a moment, with those tools in hand. Suppose a faint hint appeared that the path could drift closer than we like. What happens next is not shouting, it is scheduling. A list of telescopes is assigned time. Observers catch the object before dawn from 3 longitudes. The fit tightens by afternoon. If the hint fades, an update says so with gratitude for the extra time. If the hint grows, a second layer adds radar, if possible. If radar remains out of reach, the optical cadence doubles. The point is that every rung of the ladder is built in peacetime. No one invents it on the fly. Preparedness also lives on the ground. Air traffic advisories list a radiant and a time window if needed. The odds of a hazardous airburst stay low, but the option to route slightly wider paths over remote regions exists anyway. Satellite operators watch for streaks in sensor logs and flag nothing unusual as a calm sign. Grid managers keep eyes on solar space weather, not the comet, and make sure call centers know which alerts belong to which system. Clarity keeps rooms quiet. The same spirit guides public conversation. The safest tone is measured and repetitive. It is not dull. It is reliable. The story sounds like this. We found a visitor. We tracked it. We tested the path. We looked for changes and found none that matter. Here is when you will hear from us again. Here is a picture you can look at without any math. If that rhythm feels simple, that is the point. Simple scales. Simple travels well. As listeners settle into sleep, it may help to remember the long arc. Interstellar objects like 3I Atlas are messages from other nurseries. Their dust holds chemical clues about places our spacecraft have never seen. Their speeds map the flow of stars in our part of the galaxy. Their visits test our tools and keep our coordination sharp. Every time we track one, we learn a little more about the highways we cannot see and the rules that shape them. Most stories end the same way. The visitor brightens, drapes a pale tail across deep sky, and then grows faint as it climbs back into darkness. The charts fold. The data joins a public archive. Students, engineers, and storytellers return later to pull fresh lessons from those same numbers. Safety and science share one ledger. That is the quiet triumph of a calm, well-run watch. In the next chapter, we will translate energy into everyday terms, comparing the punch of a medium comet fragment to storms, quakes, and familiar machines. Not to spark alarm, but to set scale with friendly anchors, so worst-case talk becomes a clear picture rather than a cloud of big words. Energy is the hidden script of every impact story, so let's translate it into everyday pictures. Think of energy as the ability to do work, to shove, to heat, to shake. A rolling bowling ball has it. A gust of wind has it. When a fast object from space meets the air or the ground, it dumps that stored ability in a rush. The bright flash is motion turning into heat, pressure, and sound. Start with a modest fragment, the size of a small house, entering faster than any airplane can fly. It squeezes the air ahead into a hot, glowing sheath. If the body is fragile, it rips apart and releases its energy high above the ground. Nearby towns feel a rolling thunderclap that rattles windows. People indoors are safest if they step away from glass and wait for the booms to pass. Scale the fragment up and the tone changes. A stadium-sized core that holds together can hit the surface. The ground behaves briefly like a liquid and flows outward in a ring. A crater opens. Trees and light structures fall in circles. Close to the center, heat can scorch. Farther out, the wave is a shove that knocks people off their feet, but leaves most buildings standing. In shallow water, you see a dome of spray and a brief surge that floods low docks. How does this compare to familiar forces? Picture a summer thunderstorm that knocks out power for an hour. The storm spreads its muscle across a county for many minutes. An airburst concentrates its punch into a few seconds over a smaller area. Or think of a controlled demolition that topples an old factory. A flash, a bang, a pressure snap, then dust. An airburst is a natural cousin at higher altitude and larger scale. Earthquakes offer another frame. A mild quake rolls underfoot for 20 seconds and shifts items on shelves. A stronger one rattles dishes and cracks plaster. An impact's pressure wave can feel like the first half-minute of a quake from a single deep thud. The difference is duration. Impacts are swift. Quakes keep humming as faults slide and settle. Storms do their work by endurance, over hours and along long paths. They tear roofs, uproot trees, and flood streets. An impact does most of its work in one breath. That is why emergency managers plan them differently. For storms, you stage supplies along a forecast cone. For a potential airburst, you clear a small airspace window, remind people about glass, and prepare to inspect power lines for localized damage. Fire is a common worry. Movies teach us to expect a wall of flame. Real life is quieter. The heat pulse near a ground strike can ignite brush and dry roofs close to the crater. But outside that ring, the main hazards are pressure, flying glass, and dust inhalation. Fires start from second-order causes: a toppled stove, a broken transformer, a spark in a warehouse. Standard fire safety rules still help. Dust and debris want plain words. The grit lofted by an impact looks dramatic under sunlight. Most of it is heavy and falls back quickly near the site. Fine dust can drift downwind and make skies hazy. Simple masks and staying indoors until officials give the all-clear are usually enough. This is not toxic fallout from fiction. It is ground turned briefly into powder, then settled again by gravity and time. Sound travels far. After a strong airburst or a strike, infrasound bass notes too deep to hear can ripple around the world and be measured by distant sensors. That is science's bonus. Those waves help analysts reconstruct the event's size and altitude. They are not a hazard by themselves. Power and water systems deserve a calm paragraph. Power grids are robust against single-point hits. Crews isolate damaged lines and reroute around them in minutes. Water systems follow simple procedures. Close intake gates briefly if a nearby strike muddies a reservoir, then test clarity before reopening. Hospitals run on backup power if a substation trips. These are the same steps taken after a severe thunderstorm or a local quake. Now put numbers back in their box and use images. Imagine a dump truck full of gravel dropped from a crane onto a concrete pad. The pad buckles and dust billows. Multiply that by many cranes, and you have a small crater. Or slap the surface of a calm lake with your open hand. The slap is the airburst. The ripples are the pressure waves. The splash is the plume. Same physics, scaled up and brightened by heat. For worst-case planning, the sequence matters more than figures. First comes detection and tracking. Next come refined forecasts that pin down the corridor of any possible airburst or strike. Then come targeted advisories, brief airspace restrictions over unpopulated areas, reroutes for high-altitude flights if needed, and a short checklist for city managers in the unlikely event they are near the corridor. Finally, rapid inspection teams roll as soon as the sky goes quiet. A final human-scale note. What helps most in the rare hours when the sky acts up are small, ordinary habits. Listen for official updates. Keep hallways clear for responders. Check on neighbors who move slowly. And let roads stay open for crews. These are the same habits that help in storms. Knowing them in advance turns a surprising afternoon into a story you tell calmly later. The ocean of space is full of motion, but most waves pass under our keel without trouble. By translating energy into things your hands know, a hammer, a storm, a slap on water, you can sense the shape of rare extremes without inviting them into your sleep. We study, we prepare, and we live our days. The sky keeps moving, and we keep watch. When people hear about a strange visitor from another star, the first wave is curiosity, the second is rumor, and the third is routine. Routine keeps society steady. It is the quiet set of habits that move information from experts to everyday life without sparks. In a worst-case exercise, routine is the hero. Start with how news travels. A clear timetable calms more than dramatic language. Imagine a daily rhythm that never changes. Morning brings a short factual note. What was observed, what shifted, what stayed the same, and when the next update will arrive. Afternoon adds a single page for operators who need details. Pilots, satellite teams, utilities, emergency managers. Evening offers a simple graphic for the public. This rhythm leaves no empty space for rumor. Now look at local leaders. Mayors and school principals do not need orbital mechanics. They need a checklist. If an airburst corridor points near their region, they can move outdoor events under roofs, remind families not to gather at windows if a bright flash appears, and keep roads open for service trucks. If the corridor is over the ocean or wide desert, they simply reassure people that no action is required. The tone is steady, the checklist is short. Hospitals and clinics practice the same simplicity. Verify backup power, stock eye rinse and bandages, and expect calls about bright lights and booms. They do this for storms and quakes. Impacts sit in the same family. Rare, quick, manageable. Air traffic controllers already manage volcanic ash, turbulence, and storms. Add meteor advisories to that list. If a corridor crosses a remote region at a certain hour, a few flights step around it by dozens of miles in minutes. The change is small, the safety margin large, and passengers mostly notice nothing beyond a minor reroute on the seatback map. Satellite operators keep a quiet watch. Space is crowded, but the highest risk to satellites still comes from other satellites and small, persistent debris, not comet dust. Operators review sensor logs, check for streaks that might hint at an unusual sheet of particles, and confirm that no avoidance burns are needed. The same automation that dodges catalog debris covers rare sky events as well. Power grids and water systems focus on clarity. Dispatchers know that a pressure wave or bright flash does not cause geomagnetic storms. Those come from the sun and are announced by solar monitors. A short internal note keeps call centers aligned so that if the public reports lights or booms, staff answer with calm, consistent words. Media plays a decisive role. The best coverage is unhurried. Present facts, show paths, explain terms, and avoid labels like killer or doomsday. Replace them with visitor, path, and safe miss. Headlines can attract clicks without bending truth. Fear creates noise that can block the signal people need. Parents and teachers can turn a tense headline into a lesson. A classroom can chart nightly brightness and see how predictions sharpen. A family can step outside with binoculars and talk about dust tails. When people engage with the sky, the story shrinks from a shadow to a picture they can hold. Myths deserve gentle correction. Interstellar does not mean intelligent. A comet is not a craft. Brightness changes do not mean steering. Silence from an agency is not proof of a cover-up. It usually means the next scheduled update is hours away. A fake countdown does not become real because a video adds music. Real schedules carry dates and times you can check. Mental posture matters. Anxiety looks for certainty in a universe of probabilities. The antidote is proportion. If a risk is low and the path is watched, live your day. Keep routines. Sleep the same hours. Plan the same weekend. The sky will keep its appointment without your worry. Insurance and the economy show resilience. Local insurers treat minor impact damage like hail. Assess, repair, move on. Markets may chatter, but they settle as updates confirm a safe pass. The larger economy barely notices a sky week when the story ends in learning rather than loss. Law and policy add readiness. Countries have contact points for space objects, as they do for storms and quakes. Agreements outline how data is shared, which voice speaks first, and how airspace notices are coordinated. These wires hum quietly, so that when a message must move, it moves at once. For your own peace, keep a tiny personal plan like you do for storms. If a bright flash appears, step back from windows, indoors if possible, outside only with a wide, safe view. Keep a small kit with water, a flashlight, and a phone charger. If an evening brings a visible pass, take a minute to step outside. Let your eyes adapt. Find a patch of sky away from streetlights. A faint, moving glow may be all you see. That is enough. You are watching sunlight off ancient ice and dust from another nursery of stars. The feeling is not fear, it is perspective. The last note is gratitude. The quiet professionals who scan, measure, and post updates work through cold nights so the rest of us can sleep. Their steady schedules, careful words, and patient checks are a civic good. When the visitor fades, they archive the data for students who have not yet chosen their careers. Safety becomes knowledge. Knowledge becomes the next generation's craft. And for you, the listener settling into sleep, the message is gentle. We prepare not because doom calls, but because preparation is love made practical. The sky is wide, the earth is sturdy, and people working together are stronger than any rumor. Rest easy. The watch is kept. In the next chapter, we will return to the science and ask what 3i Atlas can teach us about chemistry in other star systems, which gases it carries, how its dust scatters light, and why those clues matter for the search for life in places we cannot yet visit. Think of 3i Atlas as a message in a bottle from another star's nursery. The bottle is the nucleus. The message is its light. When sunlight hits the coma and tail, the glow carries fingerprints of the gases and dust that escape. By splitting that glow into a rainbow, astronomers read the message line by line. Each bright or dark notch in the rainbow points to a molecule or a type of dust grain. The process sounds fancy, but the idea is simple. Different materials glow and absorb in their own favorite colors. Start with gases. Water vapor is the usual anchor near the sun, but for a cold object far out, carbon monoxide and carbon dioxide can wake up first. Detecting CO tells us the nucleus still hides very primitive ices, likely formed in a deep freeze before the parent star fully lit. Seeing CO2 says the comet has pockets that warm and vent at modest distances. Traces of methane, ammonia, and simple organics add spice. Organic here means carbon-based, not alive. These are the same simple building blocks that pepper many comets and meteorites in our system. If 3i Atlas carries a similar pantry, that hints that star-forming clouds across the galaxy cook with the same ingredients. Dust tells a different part of the story. Fine grains scatter blue light better, making the coma look slightly bluer. Larger grains reflect more evenly and can redden the glow as sunlight bounces off rough, dark surfaces. Polarization, which is how the light's wiggle prefers one direction over another after bouncing, reveals grain size and texture. Think of it like reading the grain of wood by the way it shines at different angles. From those clues, teams sketch the dust recipe: fluffy clumps, compact pebbles, or a mix. Why do these details matter for life? Because life needs chemistry and time. If interstellar visitors commonly carry water-friendly ices, and simple organics, then star-forming regions across the galaxy likely sprinkle those same seeds onto young worlds. It does not prove life is common, but it strengthens the idea that many planets begin with similar starter kits. When sunlight breaks apart some of those molecules in the coma, the fragments glow too. That glow lets us see even faint ingredients that would otherwise hide in the noise. Temperatures and distances fold into the lesson. By noting how early a comet awakens and how strongly it vents, we infer how tightly the ices are locked and how deep the heat must sink to free them. A sleepy comet that wakes late may have a thicker crust. A lively one suggests a porous, younger surface. These traits are not just labels. They show how the comet grew, how it was heated or battered in its original system, and how long it drifted in the dark before we met it. Spin adds seasoning. Small dips and rises in brightness within a night can reveal a rotation period. If the same face points toward us when certain gases spike, we know jets live in that region. Map a few of those and you get a crude weather chart for the nucleus. That chart says where sunlight unlocks certain ices and where dust layers seal them in. Over days, small changes in spin rate show how strongly jets are pushing, which loops back into orbit forecasts with better non-gravitational terms. Spectroscopy, the art of reading the rainbow, comes in many flavors. Optical spectra catch the bright features of common fragments. Near-infrared sees ices directly and senses warmth in dust. Mid-infrared reveals the vibration of silicate minerals, the same family that makes beach sand and rocky planets. If 3I Atlas shows a familiar silicate hump, its dust shares kinship with ours. If the hump shifts, the grains may be fresher, smaller, or formed under different conditions. Either way, it is a clue to the workshop that made them. There is a quiet joy in public data here. Many observatories post reduced spectra for anyone to study. Students learn to line up features, subtract backgrounds, and compare nights. Amateurs with small spectrographs can even catch broad signatures from bright comets. The more eyes that practice, the faster the next visitor's story will be read. What could complicate the reading? Clouds, moonlight, and the comet's own mischief. A sudden outburst can change the mix for a night, like stirring a pot. A split can paint two slightly different spectra if one fragment opens a fresh vent. None of this breaks the science. It adds chapters. Analysts mark the time, note the conditions, and fit models that allow the mix to evolve. From a worst-case lens, chemistry is also a safety friend. The gases we see are not toxins at ground level. Their densities at Earth are near vacuum. Their main danger is to the orbit math if jets push hard, and that danger is solved by noticing the push in the light. When production rates rise, modelers add a nudge. The path prediction sharpens again. The coma tells on itself, and the numbers follow. All these threads lead to a bigger picture. Interstellar visitors are not just tourist attractions, they are samples from environments we will not reach for centuries. With every spectrum, we test whether the galaxy is conservative or creative with its recipes. So far, the early examples suggest a familiar kitchen. If 3I Atlas adds more evidence, it pushes us one notch closer to thinking of planetary chemistry as a shared language rather than a local dialect. Imagine returning to this data in 10 years with better tools. We might notice a faint molecule today that becomes clear tomorrow. We might compare a dozen interstellar comets and find families, each pointing to a different kind of nursery. Patterns emerge from patient collections. Safety and curiosity both benefit from that patience. When you step outside and glance up, remember that the pale haze around a comet is sunlight writing chemistry in the sky. No equations are required to feel the meaning. The light is telling us what the bottle carries. We listen, we write it down, and we add it to a growing atlas of other suns. In the next chapter, we will compare 3I Atlas with the two earlier interstellar visitors that woke the world's attention, not with deep jargon, but with simple side-by-side traits you can picture as you listen in the dark. Put three visitors on a simple stage. Stage left stands the first one. The world met in 2017, a dim, tumbling shard named Oumuamua. Center stage is Borisov, the bright, classical-looking comet discovered in 2019. Stage right is our hypothetical 3I Atlas. By lining them up, we can see what makes interstellar travelers similar and what makes each one its own story. Shape and look first. Oumuamua did not wear the usual hazy coat. No clear coma, no tail. Just a skewed glint that grew and faded as it tumbled. That strange light curve made people imagine cigar shapes, pancakes, and everything between. Borisov looked familiar at once. It grew a coma and tail, like a textbook comet from another star. For 3I Atlas, we plan for both possibilities. If it looks like Borisov, we read gases and dust with ease. If it hides its gases like Oumuamua, we lean harder on how its brightness changes with time, shape, and viewing angle. Next, activity. Borisov vented strongly, which made models of its path include clear non-gravitational pushes from jets. Oumuamua showed no obvious jets, yet its motion was nudged in a way that looked like a gentle push. The leading plain explanation is that it released gas or dust in a subtle way that normal images missed. For 3I Atlas, the lesson is simple. Expect jets if you see a coma. Expect tiny nudges even if you do not. Build both into forecasts and let the data choose which matters. Composition is a calmer topic. Borisov's spectra showed common comet ingredients: water-friendly ices, carbon-bearing fragments, dust that looked cousin to what our own comets shed. Oumuamua's silence in spectra left room for debate, but nothing demanded exotic materials. For 3I Atlas, we begin with the simplest prior. Assume a pantry like Borisov's unless the rainbow says otherwise. That keeps the science honest and the public story clear. Speed and path set tone. All three ride open curves, but arrival angles differ. Oumuamua came and went quickly with little warning. Borisov gave more lead time and stayed easy to track. If 3I Atlas arrives on a brisk line close to the sun, we will have to work faster. If it enters on a higher, cooler lane, we get more nights to measure. Either way, the routine holds. Early detection sets the pace. Many hands share the load. Risk language benefits from this comparison. Oumuamua's odd light curve spawned wild ideas online. The cure was better bounds and patient words. Borisov's ordinary look made communication easier. For 3I Atlas, if it acts ordinary, we will say so plainly. If it throws a curve, we will name the curve and show what it changes and what it does not. Worst-case talk becomes realistic only when tied to concrete behaviors, not to labels. Think about fragmentation. Borisov stayed whole as far as most images showed. Oumuamua was too faint and small for clear fragment checks, but its steady tumble argued for a single body. Our earlier chapter imagined 3I Atlas splitting into A and B, then staying safe. That scenario fits the family. Splits happen in comets. They create more light and clearer tracking. They do not magically bend paths into danger. They simply ask us to track two beads instead of one. Spin adds texture. Oumuamua tumbled in a complicated way, which told us its interior was not a solid iron bar. Borisov likely spun more gently, as its coma smoothed the view. If 3I Atlas shows clean periodic flickers, we can time its rotation. If its light is smooth, jets may be masking spin. Either way, we watch for any speeding up that could hint at structural stress. A rapid change in spin is a practical eyebrow raiser because it can lead to shedding. The fix is more measurements, not more adjectives. Public perception is the hidden player on this stage. Oumuamua taught scientists to pre-write calm answers to strange light curves. Borisov showed the value of open data and simple pictures updated on a clock. For 3I Atlas, the public piece is part of the mission from day one. Post times, post what changed. Use the same metaphors every night so the mental model stays stable. Visitors on a stage, beads on a string, lanes in a sky ocean. Now fold the trio into the worst-case frame. Which one was closest to trouble by nature? None. The galaxy sends us fast, rare stones on wide mist paths. The danger is mostly in imagination, not in the numbers. The responsible way to treat a new arrival is to assume normal physics, measure hard, and keep a slot open for surprise that will be resolved by the next night of data. That mindset gives you readiness without fear. Science gains from the trio too. A strange rotator, a classic gassy comet, and a future visitor we will read with better tools. Together they turn a novelty into a comparative study. If 3I Atlas matches Borisov's chemistry, that hints at common recipes. If it behaves more like Oumuamua in brightness but still shows faint gas, that teaches us how subtle activity can hide in glare. If it does something new, the pipelines we have built will still catch it, because they were designed for change. The closing picture is simple. The first visitor challenged our expectations. The second reassured us that nature also repeats itself. The third will meet a world that now has survey lighthouses on all night, faster data sharing, and a public more used to calm, scheduled updates. On that stage, worst-case thinking becomes a checklist, not a headline. The sky sends a traveler. We watch, we learn, we sleep, and we add one more line to a growing atlas of other suns. Imagine a ladder with calm, numbered rungs. Each rung is a decision point the world would use if a future interstellar visitor ever inched from ordinary into worrying territory. The goal of the ladder is not drama, it is order. You climb as far as evidence says, and you climb slowly. Rung 1 is detection. A survey scope flags a fast mover. The message is simple. A new visitor has been found. No threat indicated. Next update at a set hour. That clock becomes sacred. If nothing changes, the update still arrives and says so. Rung 2 is confirmation. Multiple observatories lock onto the target and agree on the early path. When agreement lands, a short note explains the geometry in plain words. Independent teams cross-check. If the object is interstellar, the word visitor appears in headlines to keep tone steady. Rung 3 is characterization. Is there a coma? Are jets active? Does the light curve hint at a spin? These details feed the orbit model, because gentle pushes from jets can shift timing. The note to the public says exactly this. We are measuring how the object breathes. Breathing can nudge the path by small amounts. We will fold each new breath into the math. Rung 4 is clone testing. Thousands of slightly different futures are generated by computers using the same data. If one or two brush too near Earth, that is not a prediction. It is a cue to get more measurements. The message to pilots and satellite teams is a routine advisory that a visitor is under close watch and that the next forecasts will land on schedule. Rung 5 is precision. If geometry allows, radar joins and slams uncertainty down. If not, coordinated optical tracking doubles. The clone cloud tightens. If the tight cloud clears Earth by a wide margin, the cadence can relax. If a thin edge still grazes a safety box, the cadence stays high. Rung 6 is mitigation study. This is homework, not a launch button. Engineers pull blueprints for kinetic impactors that could change speed by a tiny amount. They also review slow pull ideas like a gravity tugboat, where a spacecraft hangs nearby and uses its own weight as a steady hand. For a venting comet, designers consider gentle heating to bias jets on one side, creating a controllable push. These are options on paper, built in peacetime, so no one scrambles later. Rung 7 is civil planning. Air traffic regulators draft a simple play if an airburst corridor ever looks likely over empty land or ocean. Power and water managers review their storm posture because it is the same posture they would use. Coastal cities confirm where they would stage pumps and portable barriers if a shallow water strike could splash a harbor. These are pencil marks on maps, not orders. Rung 8 is trigger thresholds. The global group agrees on plane conditions for the next shift up. For example, if the best fit path enters a narrow distance box with less than a certain miss, and if the uncertainty is small and shrinking, then the homework on a kinetic impactor moves from shelf to shop. The note explains that thresholds are about confidence, not fear, and that meeting a threshold only means the next step begins. Rung 9 is mission preparation. Hardware years in the making sits on a careful shelf in parts. Teams start assembly. The launch window and flight time are posted in days and weeks, not in mystery. The goal is to apply the smallest nudge as early as possible, so that a pebble of change near the start becomes a mountain of difference by the time paths would cross. Rung 10 is continuous verification. While a mission is prepared, the object is watched even harder. If fresh numbers show the risk fading, the mission pauses. If risk holds or inches up, the mission proceeds. There is no shame in standing down. A quiet stand down after honest caution is a win. Rung 11 is public rehearsal. Even if the mission never flies, a live simulation walks everyone through what would happen launch day, who speaks first, what data posts when, and how advisories would look. Rehearsal makes any real decision day feel familiar rather than electric. Rung 12 is local readiness. In the thin chance a region falls inside a final narrow corridor, simple guidance appears. Stay away from windows if a flash is seen. Expect loud booms after the light. Keep roads clear for crews. Ports move a few ships to deep water if a nearby shallow bay is part of the model. The words are short. The schedules are clear. Rung 13 is mission execution. A small, sturdy spacecraft meets the visitor early and taps it on the nose, not to break it, but to change its arrival time by a breath. That breath turns into thousands of kilometers of clean miss weeks later. Instruments on the spacecraft also send back science, because knowledge and safety travel together. Rung 14 is confirmation. Telescopes watch for the tiny change in path that proves the nudge worked. When the change appears, the world sees two pictures side by side, before and after. The caption is one sentence: the visitor will now pass well clear. Rung 15 is post-event learning. Teams publish timelines, data, and lessons. What worked? What was slow? What can be built ahead of time to move even faster next year? The archive fills with checked numbers that future students will use to write better code and design kinder missions. The ladder ends where it began, with order. Nothing on it requires panic. Each rung is a calm action prepared long before any real need arises. If 3i Atlas stays ordinary, the ladder stays on the wall. If a future visitor ever asks more of us, the rungs are ready. That is what worst-case thinking is for. It gives tomorrow a map and gives tonight a reason to rest. Picture the end of a long watch. The observatories have closed their domes for the day. Servers hum, disks spin, and data settles into neat folders with timestamps. The night crews step into pale morning and trade quiet nods with the day shift. Nothing dramatic happened, and that is the quiet victory most nights bring. If 3i Atlas has a lesson, it is that steady attention turns big unknowns into small, useful facts. Let's gather the threads. We started with a question many people hold in the back of the mind. What is the worst that could happen? We walked through impacts and airbursts, pressure waves and dust, and we did it without leaning on heavy math. Then we learned how an orbit is pinned down by simple, repeated measurements. We watched a fragment split and saw how that made tracking easier, not harder. We felt how speed shapes risk and beauty in the same stroke. We traced the invisible lanes gravity draws, and we watched how human systems ride those lanes with schedules, not slogans. From there, we translated energy into hand-scale pictures: a hammer swing, a slap on water, a summer storm. We looked at routine, the real hero of safety, and then at chemistry, where a comet's light carries a shopping list of ices and dust that ties our solar system to distant nurseries. We set 3i Atlas on a stage beside the first two interstellar visitors and learned how comparison turns novelty into knowledge. We climbed a calm ladder of decision points, each rung built in peacetime, each one a way to move forward without raising our voice. What remains is perspective. Space is not a hostile wilderness bent on surprise. It is a system ruled by patient rules. Gravity curves paths, heat wakes ice, dust scatters light. Tiny pushes from jets nudge timing. Our tools mirror that patience. Surveys scan. Clocks tick. Updates arrive when they should. The world's watch is not a single pair of eyes. It is a network of lighthouses that never sleep at the same time. There is also humility. Interstellar travelers carry stories older than our languages. They were thrown free when other suns were young. They drifted in cold for spans we measure with careful, shy words. When one crosses our sky, we get a few weeks in which to look and to learn. The gift is not only what we measure, it is the way these visits pull us into a shared focus. Radio dishes, backyard telescopes, classrooms, control rooms, all tuned to the same small traveler. That shared attention is part of safety, and it is part of the joy. You may wonder where the fear goes. It does not vanish. It changes shape. A vague dread becomes a list. Lists can be checked. A rumor becomes a schedule. Schedules can be trusted. A scary headline becomes a diagram with a clear miss distance and a date for the next update. The mind rests when it knows someone is keeping score with care. If 3i Atlas behaves like most comets, the story will fade with gentle notes. A few meteor streaks months later. A paper about the mix of gases. A graph that shows how the uncertainty shrank night by night. Perhaps a student will use the data in a class years from now. They will run new code on old light and find a small improvement, a better way to model a jet, a cleaner way to fit a split. Safety improves by inches. Science improves by inches. Inches add up. There is a practical aftertaste to all of this. Preparedness for rare sky events pays off in everyday life. A city that can route around a short, unlikely airburst corridor can also route around a wildfire, a flooded underpass, or a downed line. A newsroom that posts simple, on-time updates for a comet can do the same for storms. A family that knows to step back from windows if a bright flash appears also knows what to do in a thunderclap. The same muscles work across many kinds of weather, even the brief weather of space. Now, settle your shoulders and breathe evenly. Imagine a last, lingering look at the night sky. The visitor is a faint smear near the horizon, already dimming. A plane glides silently above a line of city lights. Somewhere far away, a dish turns, catches a last whisper, and stops. The world ticks on. The ocean of space keeps its slow tides. We set our instruments in their cradles and write the next watch schedule on the board. A final thought for those who love meanings. Interstellar comets teach two quiet ideas at once. First, we are not cut off. Materials and stories travel between stars. Second, our small, careful acts matter. A good measurement taken on time, a clear sentence posted on schedule, a practiced drill run without fuss. These are small acts that build a big circle of safety. The circle is wide enough to hold science and sleep in the same night. Thank you for listening with patience. If you step outside tomorrow and see only clouds, that is fine. The watch goes on above them. If you see stars, remember that some of those points are suns with their own debris, their own comets, their own quiet watchers. The galaxy is busy, and, most nights, kind. We will close this chapter with a promise rather than a cliffhanger. When the next visitor appears, the lighthouses will light, the schedules will start, and the same calm path will unfold. You will hear simple words, on time. You will see small pictures with clear arrows, and you will be able to tuck fear back into its box and let curiosity take the front seat again. Let's leave you with a calm, useful map you can carry after the audio fades. Think of it as a pocket guide to the sky, written in plain words. On one side is what to expect from visitors like 3i Atlas. On the other is what to do if an unusual week ever comes again. No drama, just small, human steps paired with the big, patient rules of space. What to expect. Most interstellar visitors arrive fast, glow modestly, shed some dust, and then go. Their paths are open curves that miss Earth by wide margins. If they show a coma and tail, that is sunlight waking ices. If the light curve flickers, that is spin. If the object fragments, the beads line up along the same lane, making tracking simpler, not harder. A brightening may happen. That is a jet turning on, not a steering wheel. Updates that repeat themselves are not lazy. They are the rhythm of safety. What to do? Keep your regular day. If an official advisory ever mentions a brief airburst corridor over empty land or open water, crews will adjust routes the way they do for storms. If a bright daylight flash is forecast over a remote area, the simple rule for people nearby is to step back from windows and wait for the booms to pass. If a fragment were to hit shallow water near a harbor, ports already know how to move a few ships to deeper water for an hour. These are familiar muscles. Cities flex them for weather all the time. What not to do? Do not chase rumors. Do not share dramatic posts without dates, times, or sources. Do not confuse solar storms with comets. They are different families of weather. If you see a graph with no labels, it is not a forecast. It is a picture missing its name tag. If someone says officials are silent, check the last scheduled update time. A quiet clock often means the routine is working. Why professionals stay calm? Because redundancy is strong. Survey telescopes search wide. Follow-up scopes refine. Radar, when geometry allows, crushes uncertainty. Independent teams cross-check. If the math ever lifted an eyebrow, cadence would increase. More measurements, faster posts, and, if needed, civil advisories with short, clear sentences. Even a mission study to nudge an object begins as homework long before any real need. That is the ladder you heard about. Detection, confirmation, characterization, clone testing, precision, mitigation study, civil planning, thresholds, preparation, verification, rehearsal, local readiness, execution if required, confirmation, and learning. Why worst-case talk helps, not harms. It takes fog and turns it into a list. Lists can be checked. It gives timing to fear. Clocks tame guesswork. It lets agencies share one map so pilots, engineers, teachers, and families can point to the same arrows and nod. It trains quiet skills that serve many storms. A city that can stage for a 1-hour sky event can also stage for a flood. A newsroom that posts on time for a comet can post on time for a heat wave. Practice in one lane strengthens the whole road. What 3i Atlas gives back. A taste of chemistry from another nursery. Clues about dust grains, ices, and the way sunlight breathes through a fragile body. A test of our pipelines from first spec to final, all clear. A shared moment where backyard telescopes and giant dishes look together. A reminder that science and sleep can share the same evening because the people watching are steady and the rules are kind. How to remember it. Carry 3 pictures. First, a lighthouse. It turns at a fixed pace whether seas are calm or rough. That is the update schedule. Second, a string of beads. If a comet splits, the beads stay on the same thread. Third, a soft map of lanes on a dark ocean. Gravity draws those lanes. Visitors ride them. We watch from the shore with good lamps and better logs. If you are a teacher, make a tiny project from the next visitor. Draw the nightly position on a blank map of stars. Mark the brightness, guess the spin, and compare your notes to the public archive. If you are a student, borrow a small spectrograph and try to catch the broad glow of common fragments. If you are a pilot, trust the advisories the way you trust ash and turbulence notes. If you work on grids or water, keep the comet schedule pinned beside your solar and storm bulletins so call centers stay aligned. If you are simply a night walker, look up on clear evenings and let a faint smear teach you patience. As the credits roll in your mind, picture the global relay of quiet hands that made this story ordinary. An observer in the south clicked a shutter at midnight. A student in a city posted a clean timestamp from a small telescope. A radar tech checked a dish, even though geometry said, "Not today." A programmer tuned a clone swarm so the thin threads of possibility were honest, not noisy. A duty officer wrote one sentence in plain words and pressed publish at the exact minute the public expected. None of those acts is large by itself. Together, they are the difference between rumor, weather, and real weather. If a new traveler appears next month or next year, you already know the shape of the week. A discovery note, a confirmation, a rhythm of posts, maybe a soft brightening, maybe a fragment, maybe a thin meteor ribbon forecast for a quiet dawn months later, almost certainly a safe miss measured in comfortable millions of kilometers. Then the fade. So settle in. Let your shoulders drop and your breath slow. The world is full of hard problems, but this one, most nights, is gentle. A visitor comes by. We learn its name, read its light, map its lane, and wave as it goes. You wake tomorrow to the same streets, the same coffee, the same work, and the same quiet watch above you. If you found peace in this journey, tap like and subscribe so these calm night guides keep reaching the people who need them. Your small click is part of the lighthouse, and someone far away will sleep easier because its beam stayed steady. Sleep well. The ocean of space is wide. The lighthouses are lit. The watch is kept.